A talk about something that Bruce Davis here is going to present, and then hopefully there's time for you to wander around and see what has been exhibited on the tables in the area. And at 2 o'clock or thereabouts, we'll have a gathering of panelists to talk about communes in southern Colorado in one way, shape, or form. Okay? So, take it away, Bruce. You can introduce yourself and
All right, Bruce Davis. I am an architect. It was 50 years ago, another anniversary for me as well as for Drop City. I began architecture school, and one of the first things I heard about was this madman named Steve Bayer who was doing these things out here. And it wasn't too much longer after that that I got to New Mexico and got to know Steve and started to design solar houses. So there's 200 or 300 of them out there now. I wish more of them were Zomes. So what Steve and Pat and Mike and several other people who are here today brought are some of the examples of what Zomes are about, what they have been about, and what they could be about. Specifically, we have brought along drawings and models of what a Zome house might be today with everything we know. So there are my drawings of a Zome house over there. Also, from the point of view of geometry, Paul, who's right there, you can see, has brought his wonderful toys. So you can see the giant erector set, the giant Tinker Toy structure being built across the street. And you can see at the smaller scale that you can grab yourself the Zome tool. Paul is the Zome tool guy. And that is this lovely little kit of parts that will teach you what these geometries are about. You don't need to be reading the book, you just start to put together the pieces and you'll find out what is going on. So, one of the best things you can do is just wander about and look at these things and play with them. Do people know what I'm referring to when I talk about a Zome or a zonahedra? No. Okay.
Is there a synonym with geodetic? Is that?
No.
No.
Okay, we'll start there. There are regular polyhedra. If you have any familiarity with solid geometry, which you may not, but regular polyhedra are things like a tetrahedron, which is made out of 4 equilateral triangles, or a cube that is made out of 6 equal squares, or for example, an icosahedron that is made out of 20 equilateral triangles.
With 5 bottoms.
Well, the one out there has the bottom ones missing, yes. Buckminster Fuller's geodesic geometries are most commonly based on an icosahedron or an icosododecahedron. They are derived from these regular shapes that are, in a sense, blown out into a nearly spherical form. That is particularly structural and particularly useful in certain circumstances. It doesn't easily make architecture in many circumstances because when you have a bunch of spheres, they don't stick together very well. There are other sorts of geometry in nature, like the geometry of quartz crystals, where these different pieces that are still regular geometries connect with each other, grow with each other, and they can be expanded and pulled in different directions. if you take one of these regular geometries and you discover there's a place you can slice it and stretch it, that's called a zone. So a zonahedra is one of those regular forms that has the ability to be stretched. Now, a cube can do that, obviously. A tetrahedron can't. You slice a tetrahedron, you pull it apart, you get some funny, weird pup tent shape. But there are certain shapes that have the ability to be manipulated. Those are the zonahedra. And when you look at the models, and if you play with the models, you can just see that much better than I could ever explain it. So, if you develop shapes to build out of zonahedra, these are what Steve has named zomes. Instead of domes, they're zomes. They're structures that have a particular adaptability for construction. And you can see the house over there that I designed, where two of the modular pieces are hexagonal, but one of the pieces has been stretched to show the possibility of shapes that can be generated other than purely symmetrical, purely geometric forms. But they don't lose their geometric qualities. You know, if you cut a ball in half and stretch it, you get like a Tylenol capsule, and it's not particularly anything but a funny shape that isn't structurally sound. You take one of these zonahedra and you stretch it, and you still have a meaningful, structural, beautiful geometric form. It's just like a quartz crystal. It can come in different sizes. So that probably meant something to some of you and nothing to a bunch of the rest of you. But if you look at the drawings and you play with the tools that Paul has bought, some of it may make sense. I think about the only other thing that might be worth saying here is, who has questions that you might want to bring to me, to Steve, to Paul, that might be questions or comments or disagreements? Who might have something they'd like to say?
Can I just say something first? Sorry, Bruce, you okay?
I just want to make sure that you know the importance of Steve Baer, who's sitting over here in the first row. He was involved with the Drop City in about 1967 or 68. 66 or 67. And he is the inspiration for the car top skins, if you call them that, that were put on some of the structures down there. So he, in a younger day, was climbing on top of some cars, the junkyards and that kind of thing. So he was an inspiration for that. He also helped with the solar heater. If you've seen the Drop City movie or know about the solar heater, Steve Baer. He also was involved with the cooker, which were mirrors from various cars, and to focus sunlight into like an oven or a fryer. But he told me this morning it never really worked. It was an interesting concept. He started Zomes in 1969. They have a website that employs right now between 12 and 20 people, and they manufacture passive solar equipment down in Albuquerque. He's one of the pioneer designers of passive solar devices. So he's sort of a really nice guy, and he's sitting here. Pat Gallagher, where's Pat? Stand up, Pat, there he is. Pat Gallagher and Steve came up together. Pat is an engineer. He's worked at Ford and Boeing in a former life or lives. And he is involved with what's called micro production or micro factory, which means that he thinks that people can build things with only maybe 2 to 3 employees or 2 to 3 people getting together to build. And he also, before I tell you more about that, he was a pioneer in photovoltaics way back when. So he's also an inspiring inventor and tinkerer, whatever you would want to call him. The small-scale manufacturing idea that he has been dedicated to for many years is evidenced by the tricycle that he has out by the door, which he can tell you about in person if you have an opportunity to meet him up there. He can make a recumbent bicycle for a few $100s versus the $3,000 or $4,000 that you see in bike shops. And so that's what his inspiration is, to make things available that are efficient and energy efficient and on a small scale. And he'll tell you more. I don't know if I've represented what you do, Pat.
Thank you.
And then, oh my gosh, Paul Hillebrand. Did you describe who Paul is a little bit?
A little bit. You describe further.
Well, Paul's come down from Longmont with his, I think, daughter. Is that who you're with, Paul? Liz? But Paul has a company up there called Zone Tools. And he is an inventor. And Paul was, I think, Paul, if I'm saying this right, the inspiration of the connecting device in these domes and these polyhedral type of structures. So he's been very important. Steve and Paul have known each other for a long number of years. And with Paul are some others, and I'm not quite sure because I haven't had time to get to know what they do. But Mike is here from Aspen. He's with Paul. And who else is here? So now I think, and Bruce is a major passive solar and Zome and polyhedral architect from Albuquerque. So wander around and ask these guys questions if you want, or just start with Paul. Or
Yeah, our only team member that's missing is Peter, who developed some of the geometry.
Here's a question. Let's see. Back in the 60s, mid-60s, there was an artist group at Rancho Vista in Oracle. One of those artists started building passive solar homes out of foam. And his name was Charlie Littler. Did you know him?
You know that gentleman? What is interesting about his?
What he did was he did a foam machine on a trailer, and he could drag it anywhere. And he would stick rebar in the desert floor and bend it, and then put burlap in it and spray it. And he lived in one of those structures where he had one sort of clamshell out there, and the whole face of it was south-facing. And he could open the doors during the night and get the nighttime temperature and almost maintain that temperature through the day. And we're talking, 100 degrees. Right? And it was just as efficient during the day. It was quite nice.
Lovely.
And the way he got involved in laying plastic on plywood and then running string or thin wire or something across and putting a vacuum cleaner to it and blowing it up. And then making adjustments to blow it out one side or to, making, and then it was all done to scale so that it could be done on a larger scale. It's a very interesting man.
Yeah, back there?
Yes, I'd like someone of your group to please address the subject of pros and cons or pluses and minuses of wind load factors on that structure, the civil structure.
The structures being triangulated are very easy to make strong. I don't think you'd have any more or less of a wind load issue on a polyhedral structure than you would on a pitch roof Victorian house, than you would on a flat roof adobe house. It really comes just down to anything can be engineered for the right amount of material to be strong enough. I mean, there are very few shapes that are bad in the wind. And the example is that famous bridge that was built to exactly the frequency of the wind where the bridge crossed. And within weeks of the bridge being completed, it started to do that and tore itself to shreds within a few hours. I mean, there are certain shapes that are really bad. You don't want to build in harmony with nature if the nature you're building in harmony with happens to be dangerous wind or an earthquake. If you build a structure that is too regular, an earthquake can tear through it in a really disastrous way compared to a structure that has a lot of variation. But there's no particular issue of say, zonahedral structures being better or worse than wood.
In other words, it's like an egg. It has a top point and a bottom point. And if you put pressure on the top point with the bottom point, it takes a lot more pressure than if it's set long ways, it'll bust. The other way, it'll hold its pressure. In other words, that's a structure like a dome shape. From the pressure down, will hold more pressure than what you could think that it would withstand, than what its own building structure is.
That is true if you're talking about like a perfect circle, a perfect ellipse. The matter is that in the reality of the built world, you are talking about a variety of loads. Generally, the vertical load of gravity is the greatest, larger than the horizontal load of the wind. But then occasionally in the case of something like a tornado, the wind load takes control. And also in certain wind circumstances, you have an uplift instead of a downward pressure. The result is that engineers in general design with enormous factors of safety. That rarely do you get this beautiful, pure structure that's just strong enough. Everything is massively overbuilt as an engineer calculates.
The reason I say that is when a chicken lays an egg, it has a tapered end, and the tapered end on the bottom, because when it falls out and if it was to hit, it won't break, but if it fell sideways, it would shatter.
That is absolutely true. And building houses are only as simple as getting an egg out. Strangely enough, construction for human purposes is inevitably massively more complicated than nature. We might think it's sort of simple and stupid.
Yeah, there you go, the engineer with the chicken.
You know, the engineering of nature is so beautiful and so simple, but what humans want out of a structure is so much more complicated. The result is simply everything is usually much stronger than it needs to be. Until that day, the hurricane comes, and then you're really happy.
Does the panel lend itself to being manufactured off-site? So that you can bring the panels to the job site and put them together?
You know, that is such a complicated question, and I suppose what it has to do with...
I thought it was a simple question.
Not really. I mean, if you are Elon Musk and you have enormous faith in technology, and like Mr. Musk, you believe that the future of humanity is to leave planet Earth, then definitely you are interested in manufacturing. If you happen to be someone who is deeply embedded in the dirt under your feet and you care very much about collecting materials from the site, you're going to make a different choice. You know, I think it's incredibly related to your own values. I mean, there are people who would say that perfect food can be created in a chemistry lab and sent with you to Mars. And there are people who would not want to eat anything but the weeds they can pick in a 5-mile radius. That is a matter of values and choices. There are certain circumstances where certain strategies are incredibly useful. For example, off-the-grid photovoltaic makes enormous sense and economy if you have a piece of land that's 50 miles from the nearest transmission line. It is a whole different question if you are directly next to a power pole in a state with a hydroelectric dam. That's a whole different economy. Unless you happen to believe that it is important that you can generate your own power, then it doesn't matter where. These individual strategies can each be incredibly meaningful in particular circumstances. You know, I would just as soon see panels for Zomes made in shop, because outdoors on a 30-degree day or a 90-degree day with the wind blowing is not the circumstance to get precision. And if you do want to build in these geometries, you need precision.
So one thing that was happening in the 60s, we were building geodesic domes and zones both. And one thing that Steve came up with was that the zone was good for a 4x8 sheet, and this is an economy. And the difference was extreme, really extreme. You could put up a zone in the third of the time that it would take to build a geodesic zone, because it was built 4x4, 4x8. And that's an economy that is transcendent. You know?
Pat, do you want to speak to that?
It does.
Huh?
Yes.
This man has been working on that issue.
It's very, I think that's very possible to, in a simple shop, to take and use the materials optimally with as little scrap as possible to make all the parts that Bruce needs to take his designs to the people.
With that as background, can Steve talk about a particular structure that he likes best, that he enjoys, or that he took great pride in?
Can you move the mic over?
Well, our own house, which we fixed up a couple of times, has got hexagon cluster of hexagonal floors, rooms clustered together, and those using hexagons is, I think, liberating compared to using squares. You know, we live in a huge fossil fuel culture, which is restricting us, and that's you know, a shame. But the puzzle today, for me, thinking about Rock City, the enormous improvements in all kinds of things since 1966 or 67, accompanied by almost nothing in a way. Like, you can get photovoltaic panels for practically nothing today. Electricity is almost as easy to obtain as sunlight, and yet we're doing it in such a peculiar way that benefits the banks more than the people, you know. And there's all kinds of things, like I have a thermometer here that you just pointed at a object and it gives you the temperature. And you can buy these for $50. I mean, you don't have to go to a university to learn about energy. You can buy a thing in Radio Shack and learn yourself. And that wasn't true in 1966. There's all kinds of things like that. And we're making all these wonderful tools that we could use to make things work better. But strangely, we don't seem to be doing much of it, not enough of it. So that's all I.
But while the mic is near Steve, since you were at Drop City in the early years,
Yeah.
would you want to just say something about your the philosophy of Drop City in the first few years, and Gene and Joanne Bernofsky and Clark Reckman's philosophy when you encountered them, and then how it may be perceived by many people today?
Well, you know, Gene Bernofsky was a real pioneer, and unfortunately, he's in Missoula, kind of stuck there. But I remember what Gene told me. He said the door is open. We walked in simple, and I thought that was a way to phrase the possibilities for people to do things that you can't do any better than that. That you know. That we can do things if we want it. And that was at Rock City. You could ask any question, and you had people interested in what you were doing, and that's great. But that's the only thing that I don't think they didn't have any kind of creed that I can think of.
And for those of you who don't know, Drop City is not named after dropping acid or dropping out. It was a term that Clark Reichert and Gene and Joanne Bernofsky used when they were together at the University of Kansas in Lawrence, where they dropped art from the second story or from a higher level in a building and watched what would happen with people who observed it on the ground. So it was a performance-type art concept, and they were artists and visionaries. Timothy Miller calls them secular visionaries that started Drop City. And Steve was there at that period. It later transformed. As you saw the movie, it transformed to being more drop-oriented and dropouts and Hell's Angels even and that kind of thing. Anyway, do you want to say anything else? Steve,
No, I don't.
Okay.
Is that good? Yeah, I'm Paul Grant, and I'm sort of the disciple of both Mr. Baer and Mr. Rickard. And I have to say I'm probably one of their biggest fans. I think, when I go out to lunch with Clark Rickard, who's going to be here on Wednesday, it kind of feels like going out to lunch with Picasso. Only I like Rickard's art better than I like Picasso. And Steve Baer, so Clark is the artist, the visionary that kind of made this thing happen. But Steve was the mathematician, however you did it by the seat of your pants. Steve one time explained to me, I asked him, well, how did you know, actually, can you bring that model up that you're working on? Yeah, you, come on. Because this is the model. They built they're putting together these, this looks like kind of like a geodesic sphere, right? You recognize it's an icosahedron, it's got 20 faces when he gets it finished, but you get the idea, right? It's the same as that dome we made outside, the little one, the kids played dome. And I said, well, Steve, how did you know that the length of the red line was cosine 18 of the blue line? And Steve said, well, that's where the pipes bumped into each other. He said, what I love about this guy, that's real mathematics. I think all mathematics comes from people just sort of screwing around until they say, whoa,
What's up with that, right? And then, so all of a sudden, he didn't just have the blue lines, you know, whatever this, length 1 and length cosine 18, but they also looked at the diagonal of the cube, and you got the yellow lines. And then, when he realized, this is according to you, correct me if I'm wrong, that all these lines fit together into one system, he said it was high for 2 weeks. and that's a real high, right? Coming up with an intellectual breakthrough like that, which is going to have ramifications for the next 10 centuries, as far as I can see. I mean,
It's all a fluke, you know. A fluke of not knowing any better. That's all it is. Yeah.
it's better not to know. I mean, you know, the fool, right? We backed right into it.
Yeah. Back in the-
So let me ask, what does this look like? If I hold it up, what do you see there? A cube, right? If I hold this one up, what do you see? A cube, right? What about this one? Yeah, they are. They're all cubes. They're squashed a little bit, but they're all cubes. And here's the secret. Here's the trick. This is what makes this thing amazing. It never ceases. I've been involved with this geometry through Steve and Mark Pelletier, who isn't here, and of whom Steve Baer himself said, Mark Pelletier was born knowing more geometry than I'll ever know. That's a pretty high compliment coming from him. But the nut here is that it's all cubes, right? The whole 31 zone system or 61 zone system or however high you want to go, it's really just cubic lattices that have been squashed into 3 space. For instance, the red lines and the yellow lines, well, the Clark Rickard are working with. He's working with these two. This is actually a shadow of a piece of a 6-dimensional cube, and this is a shadow of a piece of a 10-dimensional cube. You know, just like you know how 2 points make a line, right? 4 lines make a square. 6 squares make a cube. Well, you can have 8 cubes make a hypercube, 10 hypercubes make a 5-dimensional cube, and just go on forever, right? Well, that's what this guy uncovered. That he basically, and this discovery has been used by Nobel Prize winning scientists. Dan Sheckman, who got the Nobel Prize for chemistry a few years ago. Been used by the guys that discovered the fullerenes, buckyballs, and all of this new carbon nanotechnology. It's been used by top mathematicians around the world. I don't know how to say how important this discovery was, at least in my opinion. You can take it or leave it. And how important Steve Baer is. I mean, this is a great honor to be here with the man. However he did it, stumbling or with the eyes wide open, he discovered I believe it's one of the greater discoveries of the 21st century. And that was back in 1967 or 69, right? What we always say, if you're going to play with Zone Tool, there are only a couple of rules, right? Number one, if it works perfectly. If it doesn't work at all. So you don't try to, say, oh, I wish I could make this strut go over there. Don't worry, there's already one that will. Or if there isn't, you can get there some other way. You can maybe go make a zigzag path. You can always get from here to there, anywhere in this universe. But it works perfectly. The second is it's take it apart, don't break it apart, right? So kids are pretty good at building the model and then they'll rip them apart. Of course, the ends will come off and they don't work so well after that. So those are the only 2 things I tell you if you're going to go back there and mess around with them.
2 other rules.
What?
2 other rules.
You go for it, Mike.
Have fun. Don't stop.
One last thing I wanted to say is that structure we made outside is basically all blue lines, and it's a very Bristol system. I failed to bring my blue lines with me, so I hardly have any of these, but I've got the reds and the yellows, so you may not be able to mess around in 15-dimensional space, but you can have fun in 6 dimensions and 10 dimensions. That should be enough for a start.